Problem with mirrors. A 3-meter tall dinosaur is 4 meters in front of a convex mirror of a focal length of 2.0 meters. Same questions as always. Find the image distance. Is it real or virtual? Is it upright or inverted? Find the magnification. In fact, I'm going to add one more. Find the image height. Let's go through our information. 3 meters tall. So the object height is 3 meters. We know it's a convex mirror. So our crude drawing, rays are going to scatter. If it's scattering, that's already telling us we're going to have to use that backwards focal point, right? So that's important to know right off the bat. What else? Oh, that also means that means we're not going to get a real image on the left side of the mirror. So right off the bat, we know it's going to be a virtual image. And the image is going to be somewhere on this side because those rays are never going to converge. The real rays are never going to converge after bouncing off of the mirror. You'd think, are the rays transmitting or reflecting? With the mirror, they're reflecting, and as those real rays reflect, they are scattering. So you need to use the backwards focal point. I know I'm repeating myself, I do, but repetition has value. So let's get to work. And by the way, this is exactly like when you look at your Christmas ornaments, those little glassy ones where you actually like see the image in the mirror and it reflects everything else in the room. So it's something you see in regular life. It's also the same as what you see on a passenger mirror in a car. Objects in mirror are closer than they appear. It's not very horizontal, but it's close enough that I'll take it. And let's just draw a very crude convex mirror. Keep in mind, it's part of a larger circle. I'm going to try to hit everything I can remember that we discussed up to this point. Draw your central axis. And let's get to work. Oh, I didn't go through everything we know. 4 meters in front of the convex mirror. 4 meters in front, the object distance is 4 meters. The focal length is 2 meters. And I think that's all the information I have, unless I skipped something. I don't think I did. All right, 2, 3, and 4. So I'm going to use a scale of 10 centimeters is equivalent to 1 meter. So I'm going to do 30 centimeters, 40 centimeters, 20 centimeters. And I'm just writing those in so I don't forget. By the way, if you're doing this, I recommend doing it with a piece of pencil and paper or pen and paper. I prefer pen and paper. And I would use those clear rulers in the corner of the room. That's beautiful for drawing these out. Okay, so object distance. 30 centimeters away. 10, 20, 30. So that's my object distance. Focal length, 20 centimeters away, or 2 meters away. So there's my focal length. And 10, 20, I'm going to draw my focal length on the right-hand side and pretend like we don't already know which one we're going to use for rule number 2. And, object height is 3 meters. Did I not do that right? No, I drew the wrong thing. Object distance is 4 meters. Whoop. So that's going to be right there. Object height is 3 some T-Rex arms. There we go. Give him an eye so he feels a little more aggressive. Give him a tail. We have a dinosaur. And there's the top of that dinosaur. All right. This is definitely going through everything we've written, but fortunately this is the last ray tracing video we're going to do, so I don't really care. Rule number 1, parallel to the principal axis and then through the focal point. Parallel to the principal axis. And I'm going to try to match my slightly askew principal axis. And through the focal point. This is where you need to think intuitively. If this is a convex mirror, which way is this ray naturally going to go? This way, this way, this way, or this way? Yes, yes. It's going to reflect up this way. Oh, that's what I forgot to do. I forgot. No, we drew our crude mirror, didn't we? We drew our crude ray diagram. Cool. So we know it's going to go up this way. And to find the angle, rule number 1 never changes. It's through the focal point. So that's the angle that it's going to shoot up at. And because I know it's a virtual image, I'm going to go ahead and cheat and just draw these lines in so I don't have to go back and do it afterwards. Holy cow, that's hard. Rule number 2, through the focal point and parallel to the principal axis. Wait, which focal point are we going to use? Yeah. So I'm going to draw an arrow towards that focal point, and then it's going to reflect back parallel to the principal axis. And rule number 3, through the center. Oh, gotcha. I'm sorry. Once it gets to the center, it's a mirror, it's not a lens, so it's going to reflect back this way. And you notice that our 3, oh, I should have drawn arrows on these. This is going this way, this is going this way. By the way, if you draw arrows on your rays, it'll make your life a lot easier. I should have been doing that from the start. I'm sorry that I didn't. And then this is going to reflect back this way. This ray is coming in this way and going back this way. So our 3 outward going rays, bling, bling, and bling, are scattering, just like our crude diagram represented, which means we're going to have to draw virtual rays. Fortunately, we already did our first one because that was the hardest one. I kind of did it beforehand knowing that I was going to have to do it already. The second virtual ray goes back parallel, but it would also continue parallel to there. And at this point, I'm sure you've already figured out those 2 rays are enough to find where that virtual image is going to be. So our third outward coming ray is going this way, and those angles might not be perfect, but I did my best. And I'm gonna pretty good. So there's where the top of the dinosaur would be. So if that's the top of the dinosaur, rawr. Let's measure it. I think I used a scale of 10. I did. So every 10 centimeters represents 1 meter. That's about 10 centimeters tall. So I'm predicting, based on that scale, the image height is going to be roughly 1 meter tall. I think that one's going to be pretty good. The image distance is about 13 centimeters over. So I'm going to predict about 1.3-ish meters. By the way, be careful not to let your predictions look like you're just throwing an answer down. Maybe I should put predict in there. Let's math it out. 1 over SI plus 1 over SO equals 1 over the focal length. I'm not doing the math for that one. You guys can do that. If you want to pause to see if you get it right, you can. The object distance is 4 meters. The focal length is 2 meters, so 1 divided by 2 minus 1 divided by 4. Take the inverse of that, and we're going to get 4 meters. Well, that's not what I wanted at all. That's not what I wanted at all. Did I do it wrong? I'll come back.